Welcome to Chapter P. So, this is the chapter about probability. I love this chapter. It is one of my favorite chapters in your entire book. So, as a result, I actually teach an entire class called Probability. So, if you like what you see in this chapter, Probability will be offered next spring. First, we're going to start by laying down some basic probability rules. Before we can do that, as always, we need some vocab. Your first vocab word is experiment. We're going to use the word experiment loosely. So you've heard of experiments before in science class. This isn't an experiment like that. In statistics, an experiment simply means a process in which outcomes cannot be predicted ahead of time. So flipping a coin, that's an experiment. You don't know what's going to happen ahead of time. Next up is sample space. The sample space is a collection of all possible outcomes. Note that this is describing a population because we said all possible outcomes. When you have everything, when you have all of it, that's a population. Don't let the word sample throw you off. The notation for this is a capital S. So this isn't a symbol that I would ask you about on an exam. I'm not going to put a lowercase s and a capital S and make you distinguish between the two. But remember, lowercase s is the sample standard deviation, capital S is our sample space. Then we've got event. The formal definition is a subset of the sample space, but you can also think of it as a collection of outcomes. And events get their own capital letters that aren't S, so A, B, C, O, P, whatever. You get to name these whatever you feel like, and usually we do so with capital letters. As an example, consider rolling one regular six-sided die. And that's an experiment because before I roll the die, I don't know what's going to happen. What is my sample space? The sample space is the collection of all possible outcomes. So what can we see when I roll one die? That's right, I can see the numbers 1 through 6. So when I write my sample space, I write it in set notation like this. So set notation means the curly braces on the side, 1, 2, 3, and so on. And also, we're going to define an event. I'm going to call the event capital O, and I'm going to say it's rolling an odd number. So what is O in set notation? Well, look at your sample space. Which ones of those outcomes are rolling an odd number? 1, 3, and 5. So there's O in set notation. And calculating probabilities is going to be mainly a counting problem, at least at the beginning. So being able to list out your event and your sample space is helpful. When we're calculating probability of an event A, let's say, if all of the outcomes in event A are equally likely, then the probability of A is equal to the number of outcomes in A divided by the total number of outcomes. Let's go back to our example there with rolling an odd number when you roll one six-sided die. And it's a fair die, right? So all the numbers are equally likely. Well, that's the total number of outcomes in O divided by the total number of outcomes in our sample space. There were 3 numbers in O, there were 6 numbers in S, so this is 1/2. Probability of rolling an odd number is 1/2. And at least at first, in the beginning of this chapter, this is going to be how we calculate probabilities. They're just a nice counting problem. So now some more vocab. Maybe instead of just one event, we're interested in some sort of combination of 2 events. The first one is the union of A and B. By definition, this is the set of outcomes that are in either A, B, or both. So here you need to be in at least one of the 2 groups. There's the notation we use for this. What about the intersection of A and B? Definition, it's the set of outcomes that are in both A and B. So you can't just be in one or the other, you have to be in both in this case. There's our notation. The complement of A. So complement with an E, not an I, so we're not just saying A is pretty or something like that. What this means is the set of outcomes that are not in A. So the complement is everything that isn't in A, but is in your sample space. We've got notation for that as well. You'll see slightly different notation for this in different books, but this is the one we're going with. So we'll do an example. Suppose we have the set A. This set is Cardi B, Nicki Minaj, and Iggy Azalea. We've also got a set B, Lady Gaga, Taylor Swift, and again, Cardi B. What is the union of A and B? Remember, the union is it needs to be in at least one of these two things or both. So Cardi B, Nicki Minaj, Iggy Azalea, Lady Gaga, and Taylor Swift are all in at least one of those two events, so the union of A and B contains all of them. What about the intersection of A and B? Well, the only person who's in both groups is Cardi B, so the intersection of A and B is just the set containing Cardi B. And this example shows you union and intersection, but it's nice for another reason, and it shows you that these sets don't always have to be numbers. So the things in your sets might not be numerical values, and that's okay. Right, here we had people. Now we need some rules about how probabilities work. Maybe we want to find the probability of the union or the intersection. The additive rule helps us find the probability of a union. So it says for two events, the probability of the union of A and B is the probability of A plus the probability of B minus the probability of A intersect B. I'll also pause here to say that there are multiple ways you can read some of these statements when you're translating from probability statements to words. So the probability of A union B is often read the probability of A or B. And the probability of A intersect B is often read the probability of A and B. So I will be switching between the two of those most likely, but they're the same, so get used to seeing both of them. And back to our additive rule, the reason we have to do the probability of A plus the probability of B minus the probability of both is because we need to subtract off anything we could be accidentally double counting. Now, if two events A and B are what we call disjoint, that means they have nothing in common. You also might see this referred to as mutually exclusive. If two events A and B are disjoint, then that means we can tweak our additive rule slightly because we don't need to subtract off the probability of both because there's nothing that they have in common. So the probability of A or B is just the probability of A plus the probability of B. So ignore that. Typo. Examples on the next page. Again, we're going to consider the example of rolling one regular six-sided die. Let the set A be you roll a 1, 2, or 3. Let the set B be you roll a 4, 5, or 6. And let the set C be you roll a 2 or a 6. What is the probability of B or C? AKA, what is the probability of the union of B and C? We use our additive rule, so that's the probability of B plus the probability of C minus the probability of both. Well, the probability of B, there are 3 things in B, so 3 out of 6. Where's the 6 come from? Our sample space had 6 numbers in it. The probability of C is 2 out of 6. And the probability of both, well, let's see. There is a 6 in C and there's a 6 in B, and that is the only thing they have in common. So that probability is 1 out of 6. So doing that math, we get 4 out of 6, or 0.667. Continuing this example, there's our setup again. Now we want to find the probability of A and A or B. So now we're looking at A or B. And what's nice about A and B is we look at those. A is 1, 2, 3, B is 4, 5, 6. They have nothing in common. They're disjoint. So when we do our additive rule here, we don't have to subtract anything. We can just say this is the probability of A plus the probability of B, or 3 out of 6 plus 3 out of 6, which is equal to 1. And you might be thinking 1, like that might make you a little uneasy, but it's okay. The probability can equal 1 sometimes. Probability just needs to be between 0 and 1. And the reason this one is 1 is because A and B expand your entire sample space. So we've now accounted for 1, 2, 3, 4, 5, and 6, which were all our possible outcomes. So when you account for all of your possible outcomes, the probability of seeing at least one of them is 1. Now, the complement rule. So for an event A, the probability of A complement is equal to 1 minus the probability of A. That's because it's implied that the probability of A plus the probability of A complement is equal to 1. And that's because your sample space can be split into two things that are in A and things that are not. Next up, we've got conditional probability. So for two events A and B, where the probability of B doesn't equal 0, because we're going to divide by it, the probability of A given B, so that's how you read that, the probability of A given B is equal to the probability of A and B divided by the probability of B. So this is the definition of a conditional probability, and this is going to be very important for us. These are tricky to work with, and they're important, so this is something I recommend making sure you understand. Note, the probability of A given B is not the same thing as the probability of B given A. So that's a really common misconception, but I've got a cute example here with some cute baby polar bears to help us remember. So a fun trivia fact is that a lot of polar bears are twins. So a lot of polar bears are twins. That means the probability of being a twin, given that you're a polar bear, is very high. But there are plenty of twins who aren't polar bears. You might be a twin, and you are not a polar bear. So the probability of being a polar bear, given that you're a twin, is very low. So clearly, if one of those is very high and one of those is very low, those are not the same probability. So we've got an example here to deal with conditional probabilities. In a group of 100 people who recently bought a sports car, 40 of them only bought an alarm system. We're going to call that A, and we're going to make things purple. 30 of them only purchased bucket seats. That's going to be a green B, and 20 purchased both an alarm system and bucket seats. So if a car buyer chosen at random bought an alarm system, what is the probability that they also bought bucket seats? We'll make a Venn diagram. In this one, it's not super helpful because they were very explicit in their wording that 40 only bought blah, but sometimes the wording of these can be tricky, so it can be very helpful to make a Venn diagram and see just exactly how many you have in each group. So we've got 40 that only purchased alarm systems, 30 that only purchased bucket seats, and 20 that purchased both. So I want to know if a car buyer chosen at random bought an alarm system, what is the probability they also bought bucket seats? Before you can calculate this probability, the first thing you need to do is write your probability statement. So that's the thing on the left. Every good probability has a probability statement. So that is something that I am grading for, and it's something that can be a little tricky translating between words and probability statements, so definitely recommend practicing that. So here, a car buyer chosen at random bought an alarm system. So that's what we know. So we're going to say that's the given. So given that they bought an alarm system, what's the probability they bought bucket seats? So that's how I end up with the probability of B given A. So the probability of bucket seats given alarm system. Then we just use our definition. So 20 out of 100 divided by 40 out of 100 is 1/2. Got a couple more rules. We have the multiplicative rule. So the multiplicative rule there says the probability of A and B is equal to the probability of A given B times the probability of B. And the probability of B and A is equal to the probability of B given A times the probability of A. These are equivalent. These are equivalent reorderings of the same statement. So if you take your definition of conditional probability, you flip some things around, you're going to get these two statements. So that's where they came from, and they are saying the same thing. Because the probability of A and B is equal to the probability of B and A. So A and B, B and A, those are the same. We also have this idea of independence. So intuitively, independence is that knowing that event B occurred doesn't change the probability that event A will occur. So if you know something about B, that didn't give you any information about A. So symbolically, what that would look like is if A and B are independent, the probability of A given B is just the probability of A. So knowing B didn't change the probability. And our multiplicative rule here for independent events, we just change those conditionals. So now in the first one, instead of the probability of A given B, I just have the probability of A because I know that knowing B didn't change anything. And again, these are two equivalent reorderings of the same statement. And note, independent events and disjoint events are not the same thing. So it's another very common mistake to want to make, but disjoint and independence are not the same. Furthermore, they are so different that they actually cannot happen at the same time. So something cannot be independent and disjoint. And that is a very fun, we won't go over it here, but that's a very fun little proof that you can do. If you like proofs, it's like a little puzzle. So that brings us to the end of section 1.